On that last question on the homework, talking about this one, right? The Palladium question. Are you familiar with the idea of half-life of radioactive material? Half-life, yeah. So the idea is you have some, after a certain amount of time, it always loses half and half and half and half. Why is this a useful thing to model? Why is half-life a useful characteristic to model? What? You can tell how old things are. You primarily see this in the terms of, what's it called? Something dating?
Oh.
Carbon dating. Yeah, carbon dating, exactly. You measure the amount of carbon in something, and then you can use a formula to figure out how old it is, because once something dies, it starts decaying, right? Kind of makes sense. We start with 1 kilogram. So on day 0, so how much is left? 1 kilogram. On day 4, how much is left?
Half.
Because it's 1 times 1/2. 8 days later, it's 1 times 1/2 times 1/2. 12, it's 1 times 1/2 times. Keeps on halving. And what's the last one? Do you notice a pattern? Okay, so how many times am I multiplying by 1/2 here? Well, 0 times. 1, 2, 3, 4. What you're trying to relate are these numbers. What's the relationship that you see? How do you turn... It's 1/4 of it, exactly. So your mass in terms of time is going to be the starting amount times 1/2 to what power? It's in terms of t. Divided by what? Yeah, 1/4 of t. Or another way to write that would be t over... We can clean that up a little bit because the 1 is invisible. It's a convenient number to start with. So our mass in terms of time, days, is going to be 1/2 to the t over 4 power. Exactly. Now, if we wanted to invert this, what do you need to do? Well, yes, but what's the first step? Nope. Switch m. So we get t is equal to 1/2 to the m over 4. Now here's the thing. In order to go significantly further, in order to solve this, you would need to use logarithms. Do you feel as though there's a use for logarithms now, even though you don't know how to use them yet? Yeah, you can solve things like this. If you kept on going, this is what it looks like. There is one thing you can do without using logarithms to clean this up a little bit. You could raise both sides to a power. What power should I raise them to? Yeah, let's raise it to the 4th. Because if you do that, it turns into t to the 4th is equal to 1/2 to the m power. But you need to isolate m. You need logarithms in order to do that. When you're done, you end up with time in terms of mass, right? Time in terms of mass. Why is this something that's useful to have? Well, what did we state as our original? It's the inverse, and that allows us to do things like based on how much is left, which is called, when we call it, carbon dating. Why do we do carbon dating instead of palladium dating?
Because carbon's more common.
Carbon's in which things?
Alive things.
Things that are alive. We are carbon-based life. Interesting thing about carbon, well, not just about carbon, but interesting thing about carbon is it's really, really, really close to, I'll give you a hint, everybody. It's by, I don't remember why exactly, but essentially we could have easily not ended up carbon-based life forms. We could have ended up as, anybody know? Oh man, I can't be the only one who reads science fiction and learns about this stuff. We could have very easily ended up as silicon-based life forms. Its chemical properties are almost identical to carbon. Anyway, so...
Would that have changed anything?
That's interesting. You could look it up. The thing is, as far as people understand, they don't really have anything to study, considering they don't have any silicon-based life forms yet, which we could easily find. Our basis for life is carbon. Point being that, by all accounts, nothing substantial would change. We could be exactly how we are, but with silicon instead of carbon. As far as I understand, I'm going to go on the right. As far as I understand it, I could be wrong. It's an interesting thing to think about, though. When we search for life, life could be based on something else. But since carbon is in everything, there's a certain amount that stays the same. But when the life form dies, tree gets cut down, becomes fossilized. When an animal dies and the bone dies, you can carbon date things and find out pretty accurately how old some items are. It's pretty neat, actually. It's pretty cool. Okay, what about on the homework? There's one other one that I think you probably had issues with. Which one do you think I think you had issues with? 5, 6, 7, or 24? No, you guys did 7. 7's like a two-step thing. Yes, I understand you might have hiccuped over the fact that you didn't remember sine inverse. Which one? There's no number 4. 24? No, you know how to do that. 5. 5's the one I think you guys ended up with problems. I think you did, because 5 you end up with this. What is it? 10, what is it? 4 minus 3x squared, so nothing like that. Okay. 4 minus 3x squared. They ask you to find the what? Domain and range. First of all, finding the domain is a little bit tricky. You just have to be careful. This is what I think you might have messed up. What do you have to make sure happens? When you want the domain when the domain dictates, it's the set of all input values, the legal values. So what has to be true? What do you have to watch out for? Is any division? We want to avoid that. Yeah, exactly. The negative numbers underneath the radical sign. It's an even root. So we want to make sure what is positive. 4 take away 3x squared has to be greater than 0. That means that 4 has to be greater than or equal to. So 3x squared has to be less than or equal to. So x squared has to be less than or equal to. This is where you need to be really careful. What might you do at this point? Square root it. You have to be very careful, because when you square root this, you do end up with x, and you end up with 2 over root 3 on the other side. And that is correct, but there's something we need to put over here, because when you square something, it is always what? Plus or minus. So what can we put around the x here to make this proper? Absolute value, yeah. If you do that, that is correct. This means that x has to be less than or equal to 2 over root 3, or greater than or equal to what?
Negative 2 over 3.
Yeah, and another way to write that would be negative 2 root 3 over 3, less than or equal to x. Why do we generally write it like this instead? Yeah, downstairs, I like that. Yeah, we're not... Downstairs? Mr. Weston? Yeah, I see that being Mr. Weston. We don't really like irrational numbers in the denominator. That's a very pre-calculus term, like before calculus. When you get to calculus, it matters less. But they're the same. Point being, if you had just written this, is it just correct to write x is less than 2 root 3, like that? No, because can x be negative 10? No, x has to be greater than negative 2 root 3 over 3, because if you square it, it still has to be less than 2 over root 3. So, you now have the domain. What might you have done next to find the range? What were you programmed to do to find the range? Find the domain of the inverse. We could find the domain of the inverse. Before you launch yourself in finding the domain of the inverse, which is what you're programmed to do, please just do a reality check on this. If you have your calculator, what's a really cool thing you could do? Graph it. So let's actually graph this and see what it looks like. It's too what? It's too steep right there. It has a little freak out. Point being, this is an arc. So what do you think the range is? It has to be greater than 0 and less than 2. Yeah, let's look at this logically. Let's go back. Don't forget basic logic is what I want you to get at here. Can you plug in... when you plug in values in here, you know it has to be between, it has to exist inside the domain there. What's the smallest you can make that? What's the smallest you can make that? No. Just the 3x squared. What's the smallest value you can make that? 0. The smallest value you can make it is 0. Plug in what? 0. So what's the biggest this can be? 4. What's the square root of 4? 2. You okay with this, everybody? What's the smallest you can make that?
0.
What's the biggest you can make this?
4.
What's the square root of 4? So the range here is actually what? Y such that greater than or equal to and greater than, less than or equal to 2 and greater than or equal to 0. Absolutely. That's what they're asking you for. Did they ask you to find the inverse? No. We have a technique, though, that allows us to find the the range of a function by finding the domain of the inverse. The problem here is, look at the graph here. Here's our graph. What's the problem with finding the inverse of this thing? What's the problem with, if this is the function right here, what's the problem with finding the inverse? This is f of x. What's the problem with finding the inverse? What type of function is that? Not necessarily. It's not, it looks like a quadratic. It's not what I'm asking you about. What's unit 4s on two topics? What are they? It's not 1-to-1. This is not 1-to-1. So if it's not 1-to-1, what does that mean about its invertibility? Not invertible. If you invert this, you can actually find the inverse, but the inverse is not a what? Exactly. So we say, when you say something isn't invertible, it means that the function, it's not a 1-to-1 function. If we wanted to make this invertible, what could we do to this function to make it invertible? You could cut it off by limiting its domain. So let's just pick the positive side to this, because that's what I have typed into my calculator, and I like dealing with the first quadrant as opposed to the second quadrant. So what do we want to get rid of? We want to get rid of that. So if we go back to our calculator, what do we plug in here for over here? Yeah, you do the parenthesis, make sure you go all the way over parentheses, second math, 3, x is greater than, oh, gotta do x, second, wish I could actually type, second math, greater than what? 0. And now when we graph it, look what it does. Is that a 1-to-1 function?
Yeah.
Yes, it is, yay! So let's also, now let's turn on y equals x, and we need to flip it over that. And it does, there's no gap there. We're okay with that? So let's go back and numerically find the inverse, though. We have this. Do you have practice finding an inverse like that? Do you have practice? Yeah, we did it yesterday. We did a couple. Well, I did one in particular. What's our first step if we want to find the inverse? We switch. Now we need to, oh, x squared is equal to what? So 3y squared is equal to? So y is equal to plus or minus the square root of 4 minus x squared all over 3. Now, is it positive or negative? Let's look at our graph here. If that's our graph, the yellow, if we want to go ahead and graph, if we wanted to graph, just graph the inverse, what do you draw first? You draw y equals x, and then we need to flip it. What's it going to look like? It'll look vaguely like that, right? Actually, it should cross right here, right? Vaguely like that. What's the range of that function? Positive or negative?
Positive.
The range is positive, so go back over here. Which one do we need to choose? Yes, we need to choose that one. So if we graph this, which I've already, conveniently typed into the calculator. If I graph this, look what also comes out. Yay! Did that work? Yeah. I had to do something to this inverted function, though. What did I have to add to the end here? X needs to be less than 2, and it needs to be greater than 0. You actually have to add in domain restrictions, because if I take away this greater than... Actually, I'm going to take away all the domain restrictions here. Let's see what happens. If I take away all these domain restrictions and I graph this, look what happens. We get the original function, greater than 0, y equals x, and then... Ooh, do we want that? No, what do we want to get rid of? We want to get rid of that left side, right? Why doesn't it graph anything greater than 2 over here? We'll go back and look at the function, everybody. Can you plug in something greater than 2 right there? Because if you do, what happens to the radicand? Do we like negative radicans? No, not underneath even roots. So what we do is we go under here, and we say that x has to be greater than what? X needs to be greater than 0. We don't have to say anything about less than 2, because the function is automatically not graphing anything with x value greater than 2, because it's not in the domain. Is this graph capable of graphing imaginary numbers? Not as such, no. So that worked pretty well. So the main point I'm trying to get across is paying attention to the domain and range pretty important when dealing with inverse functions? Yeah, it's very. So what do we have right here? We have, here's f, and we have, well, I'll try to draw a better arc here, g. And this is y equals x. Now, there's an important function on your calculator for graphing. If I go to y equals, if I go to, sorry, window, and I just change this to -4 and I graph this, if I flip that over the line y equals x, does it look like they'll overlap? Not really. Can someone tell me why all of a sudden it looks like they won't overlap? The scale is different on the x and y axis, right? If you want to automatically easily make the scale the same, window, sorry, zoom, you see square right there? It picks the largest value, and you see the distances between the x values here and the distance between the y values. You see how they're the same? Zoom square is really helpful if you're dealing with inverse functions. Did I tell you about this? One of the inadvertently hardest questions I've ever given. I gave a graph and I said, please graph the inverse of this, but the scale was different on the x and y axis. Do you know how hard that is to do visually? To flip something over the xy axis? You have to graph it, do it point by point and connect it. It is really hard to see. The reason it was hard to see, or why I ran into it, is I tried to make the answer booklet and I couldn't get it to work. It just wouldn't work, and I realized because the scale was different. So have the scale be the same if you're graphing inverses. It'll be very helpful. Do we feel okay about that? The first thing you're going to do? Yeah. There's something approximately like this. Nope, that's not what I wanted. Right there, right? That's not bad. It's pretty good. So then it's going to cross there too, so it'll look something like... Ooh, that's not good. Like that, right? Maybe a little more. Approximately like that, right? So that would be F inverse, right? How do you go about graphing 1 over? Make a table, right? You make a table, so what points stay the same? 1, 1, and any other ones stay the same?
No.
No. This graph is just going to go down again, right? Like that? Yep. Cool. Okay, so let's talk about this one, though. You must love this. So, did you like this one? No, you didn't? Oh, come on, it's such a fun one. We did it yesterday and today. Oh, it's so much fun. What's your step 1? Yeah. Now what? Oh, let's square it. And then you end up with y squared plus 3y minus x squared is equal to? And you're like, gosh, I can't factor that. What does it look like? Yeah, so what are you going to use? Quadratic equation, quadratic formula. Yeah, you are. What does A equal? B equals? C equals? Negative x squared. Yeah. So then you do b squared minus 4ac. That's called what? Yeah. So you end up with 9 minus 4 times 1 times negative x squared. So what do you end up with? 9 plus? So what does y end up equaling? Negative 3 plus or minus the square root of what? 9 plus 4x squared all over? All over what? 2. That's correct. Now, I gave you some of the domain. Are x is greater than or equal to? 0. So, do you remember which one you're going to have to choose, the positive or the negative? How do you go about doing that? Well, this is always going to be what? The radical is always going to be what? Itself is always going to be what? Positive. There's no way to square root something and get a negative, right? So we have to choose which one we want. Why can't we have positive and negative right there? It would make it not a. Yeah. So you need to choose one. So if we have negative 3 minus a positive number, what's it always going to be? Well, yes, it's always going to be negative, right? It's always going to be negative. So which one are we going to choose? The positive one. We're going to choose the positive one, mainly because the original function is always going to be positive. So our inverse is going to be negative 3 plus the square root of 9 plus 4x squared all over 2. Now you might be worried, can this thing be negative? Well, that negative 3 might make it negative, but let's look at the radical here. What's the smallest value? What's the smallest value this can be? Nope. Square root of 9, which, yeah, so what's the smallest thing this whole thing can be? 0. Is there any way to make this thing negative? No. To make it negative, you need to make the numerator negative, right? Is there any way to make the numerator negative? No. So, in this case, we have this, and what's the domain? X is greater than what? Or equal to? 0. Can it be as big as you want? Sure. Sure. Absolutely. It's pretty cool. Are you liking these, or what? What do you think?